Continuing where we left off with solving equations, in this section we're going to focus on solving inequalities. So remember that solve means to isolate the variable. So to find out what value the variable has. And we can do that whether we have an equation or an inequality. It doesn't matter what the symbol in the middle is. So we're going to use the same tools. We're going to follow our order of operations, but in reverse in order to solve these inequalities. So starting off, it says the speed limit in front of the school is 20 miles per hour. Any speed over this limit will cost you a hefty fine. What expression could be written to represent the speed you can travel without a fine? So first of all, this is an inequality. We know that because an equation has one solution. Not always, but we saw a case where there's infinite solutions or all real numbers, but in general, equations have a solution or a number for the variable, whereas inequalities have a range of values. So we can have lots and lots of solutions. In this case, any speed above 20 miles per hour would be too fast. So we could say that the speed is, well, let's see, speed that you can travel without a fine. Okay, so S needs to be less than or equal to 20 miles per hour. So on a number line, we can represent that if we say that this is, say, 0 near the middle here, and we could count by, say, 5s. So this would be 5, 10, 15, 20, 25, 30. Then we can represent that on a, shouldn't have blackened that in. I was just trying to show where I was putting 0. So the point we care about is 20 miles per hour. That's right here. And we have two options when we draw a circle or a dot at the number 20. If we draw an open circle, then it does not include that number. So that means we can't go exactly 20 miles per hour. Whereas if we fill in the circle, then that number is included. So in this case, if the car is going exactly 20 miles per hour, then we're okay. So we're going to fill in that circle and make it solid to show that it's okay to go 20 miles per hour. And then to show numbers less than, so our speed is less than 20, we're going to draw an arrow going to the left on our number line. I'm going to grab a different color here so we can see it a little better. So we're going to draw to the left an arrow going this way, saying that all values below that are okay to be traveling. So since this is a real world problem, we actually get to look at our first insight into a topic called domain, which tells us the reasonable values that our variable can have. So not only is S going to be below 20, we know that the slowest a car can go is 0 miles per hour. So I could actually draw this a little more completely and more accurately by saying the car can go between 0 and 20 miles per hour. So the lowest speed I can go is 0, and my speed is bigger than that. So reading my inequality symbol, I'm on the bigger side of that symbol here. And then S is less than 20 because that's the most I can go. So I can be going exactly 0, so I'll fill in that dot, and then I'll draw in the segment connecting those to show that those are the speeds that I could be going. So if we said S is less than or equal to 20, that would also convey the right message, but since this is in the real world, we should consider that there's a limit on the other end as well. All right, so an inequality is a set of two expressions. Remember from our last notes, expressions are some mathematical information made up of constants and variables. And these have an inequality symbol between them. Inequality symbol. So inequality symbols, hopefully you're familiar with, they compare two values. So if I have this and I say A and B, I read this as A is greater than B. If I read this one, A and B, it's A is greater than or equal to B. So when we add this little symbol underneath the inequality comparing symbol, then what we have is that's basically part of an equal sign. So it says that A can be that value. So our inequality above used that symbol to say that our speed was greater than or equal to 0. But it was written the other way around. So if I write A is greater than or equal to B, or B is less than or equal to A, these mean the exact same thing. So what I do is I focus on where is the small end of this symbol and where is the bigger end of that symbol. So over here is the big end. Some people talk about this as an alligator eating a number. I just think of it as the smaller number is on the small side of the symbol and the big number's on the big side. So if I put it this way, this is my small number and this is my bigger number. If I put it this way, this is my small number and this is my big number. So again, hopefully you're already familiar with those. This symbol, A and B, we read as less than. A is smaller than B. And this one we read as A is less than or equal to B. Yep. So solutions to inequalities are not a single number. They're a range of values, meaning every solution to an inequality has infinitely many solutions. In our problem up above, I could be going 2 miles per hour, I could be going 12 miles per hour, but I could also be going 11.372 miles per hour. It's a continuous range of values, meaning that there are infinite solutions. So we can't list them out. We can't say the solution is 7 or 12. There are infinitely many of them, so we have to use this range representation to talk about what they are. Okay, for this inequality, so now we have one that looks more like an equation. So pretend this was x minus 6 equals 4. We're going to solve the inequality in exactly the same way that we would solve that. And since we have here a subtraction operation with our x, then we're going to need to add 6 to both sides of this, and then we're left with x is greater than 10. So it asks, is x equals 3 a solution? So it's asking, is 3 bigger than 10? No, 3 is not bigger than 10. Is x equals 10 a solution? So is 10 greater than 10? No, 10 is equal to 10. So that's the difference between greater than and greater than or equal to. We do not include the 10 here. Is x equals 12 a solution? Yes. 12 and any number bigger are solutions. We would represent this by putting 10 somewhere, so say here. We're going to use an open dot like we talked about up above. So the open dot means that it cannot be 10. So I think of it like an incomplete symbol. So this symbol is missing the middle. So this is missing that value. And this one with the middle filled in, it includes that value. So this symbol is incomplete, this symbol is complete. Then our values are greater than 10. Greater on the number line is to the right, so we're going to draw an arrow to the right, showing the direction that our solutions lie. And remember, we can't list out all the solutions because there are infinite solutions. All right, so there's words that we use to represent these. Hopefully you're familiar with some of these. So we use words like more than or greater than or more, greater, above, no less than. So some of these go together, like this is That's not no less than. Whoops. That would be the next one. More, greater, bigger. Yeah, words like that. Words that mean bigger numbers. Greater than or equal to could be things like at least. So if I need $100 to buy something and I have at least $100, then I have enough. So words like at least represent this greater than or equal to, and then no less than. So that's kind of the opposite of this one, which is less than. If you think about on a number line, if I have one thing that is less than, so this and to the left, then the other side of that, greater than or equal to, would be here, and that would be the opposite of that thing. So that one is everything to the left of a number, and this is everything to the right, including that number. So things like that, we end up with things like a minimum. No, that's not minimum. Minimum would be... yeah, minimum would be that, I guess. So if I have a minimum of 5 people, that would be greater than or equal to 5. This one could have a maximum of that. This could be no greater than. There's lots of words that we use to represent these in word problems, so I think you hopefully get the idea. Yeah, so this could be less than, below. Yeah. Okay, we're gonna move on. So Ray's dad told him not to turn on the air conditioner unless the temperature is at least 85 degrees Fahrenheit. So there's a key word, at least, is going to help us figure out what symbol to use. So at least means it needs to be 85 or greater. So our temperature needs to be greater than or equal to 85 degrees Fahrenheit. So greater than or equal, yeah, we put at least right there. Good. So define a variable. I define my variable as T. So T means temperature. It's good generally to pick a meaningful variable. T, capital T, is used throughout science to mean temperature, so I picked that. Write an inequality, so we wrote that T is greater than or equal to 85, and then graph those solutions. So 85 will be here. He can turn on the thermostat if it is 85. That's inclusive, so we'll blacken that and darken that in. And then we'll say all temperatures greater than 85 degrees Fahrenheit. So that means if the temperature, and to double check ourselves, so this would be like 90, 95, 100. So to check your reasoning when you look at your number line, ask yourself, if the temperature is 80, can Ray turn on the thermostat? No. Or turn down the thermostat? No. If it's 75, can he turn it down? No. Over here on this side, which is included in our solution, he can turn it on at 90, 95, 100. The higher the temperature goes, it's okay. There's probably some upper limit that we would actually reach because you can't get, you get to like 120 degrees, Ray's probably melting, but, since we're not told what that maximum temperature is, we'll just say it can go up without limit. A cell phone plan offers free minutes for no more than, so that's a key word, no more than 250 minutes per month. So no more than is this, right? Greater. So no more than, the opposite of that. So no more than would be less than or equal to. That's the opposite of greater. So our limit is 250 minutes per month. Define a variable. So here I'm going to use M for minutes. I could use lowercase t for time. But I'm using M for minutes. and write an inequality for the possible number of free minutes. So m in this case, our comparator, is less than or equal to 250. On a number line, we're going to have 250. We can include that value, so it's less than or equal to, so we'll color in the dot. And then our arrow is going to go to the left. In this case, there's a definite lowest limit of how many minutes could be used. So this would be a very basic answer. A more complete answer would be to say that m is greater than or equal to 0 and less than or equal to 250, because there's no way to use less than 0 minutes. So if I wanted to make that a really robust and complete answer, I would have 0 over here with a closed dot, 250 over here, and then all the values in between. Keep in mind there are still infinite values here, everything in between 0 and 250. So if I used 3 minutes or 3.17 minutes, there's infinite numbers between any two numbers on the number line if it's continuous. Inequality rule. When solving inequalities, the only thing different from equations is if you multiply or divide by a negative number. So this is the one difference with how we do things between equations and inequalities. The example here shows if we divide by -2, then the inequality switches from a less than to a greater than. There are actually two ways to do this problem, so I'm going to go through both. This is the normal one. So what we would do in this problem is we have the x's on the left. So the first step we do to get rid of, so we have an addition. We've added 5 over here, and we've multiplied by 2. So step 1 is subtract 5 from both sides. That gives us -2x is less than -10. And then the next step is to divide by -2 on both sides in order to get rid of that coefficient. But in this case, since we divided by a negative in an inequality, we need to make sure we flip this sign the other way around. So now we have x is greater than +5, and that is our answer. A different way of thinking about this is to avoid multiplying by a negative or dividing by a negative at all. So let me write this out a different way so you can see that it comes out the same. So instead of making negative x's, I'm going to move the x's over to the right side by adding 2x to both sides. That's okay, we can add that to both, and it doesn't matter which side the x is on. Now I have 5 is less than 2x minus 5. Now I need to get this 5 over to the other side, so we do +5, and we end up with 10 is less than 2x. And then my final step here would be to divide by 2, but I'm dividing by a +2, so I don't need to worry about dividing by a negative. And I end up with 5 is less than x. 5 is less than x, remember, is exactly the same thing as x is greater than 5. These two things mean the exact same thing. It says x is the big number and 5 is the little number. So there's two ways of doing this, but if you multiply or divide by a negative, you have to flip the inequality sign. You technically don't ever have to do that. You can use addition and subtraction and move the x's to the other side. But by convention, we do prefer to write x on the variable on the left. So if we end up getting 5 is less than x, we want our final answer still to be x is greater than 5, so that we are solving it in terms of x with x on the left. I hope that makes sense. Okay, to solve an inequality, use the same steps. So we follow everything we talked about previously. We do distribution, combining like terms, inverse operations in reverse order, and then remembering this one special trick, which is to flip the inequality if you divide or multiply by a negative. Common misconception here is, remember, this is only multiply or divide by a negative. So if I had 2x is less than negative 10 and I divide by 2, I do not flip the inequality symbol because I divided by a positive. I didn't divide by a negative. Divide by a negative. The other thing that people sometimes mess up is if I have like 2x minus 2, need an inequality, is less than or equal to 8. Let's say 2x plus 2. Here where I do minus 2, they say, well, I did something negative to both sides and I want to flip that. But we don't do that because this is not a multiply or divide operation, so there's no flipping. It only happens with multiplying and dividing. And then finally, if we have special cases like we talked about in the last section, anytime I end up with no variables, so remember that these two things, special cases, only happen when all variables cancel. And then we have the same two options that we had for normal equations, which is if we get a true statement, then all real numbers are solutions, so we put all real numbers. And if we get a false statement, we have no solution, so we put no solution as our answer. So let's look at two quick examples of that, and then we'll do this last one to wrap up. So if I had something like 3x minus 5 is less than 3x plus 2. When I try to solve this, I'm going to subtract 3x from both sides, and then I end up with the statement, negative 5 is less than 2. So I have to ask myself, is that true or false? So I say, is it true? And in this case, it is. Negative 5 is less than 2. So if I think about my number line, 2 is over here. Negative 5 is to the left of that, so it's less. So in this case, I would put x is all real numbers. Then if I had an opposite case to that, so if I had x plus 7 is greater than or equal to x plus 12, then when I try to solve that and take away x, I end up with 7 is greater than or equal to 12. And I ask myself, is that true? Is it true? No, not true. This one was true. 7 is not greater than or equal to 12, so for this one I'm going to put no solution as my answer. I don't need the quotes, just putting no solution. Okay, so last problem to wrap up these notes is this more complicated looking one that has distribution and multiple steps involved. So let's go through this one. If we follow the like our normal order of solving, we're going to distribute first. So I'm going to multiply this 2 by the x and the 1. Remember that I'm not doing any inverse operations, so nothing else changes. All I'm doing is rewriting this part with the 2 multiplied out by these two things. Everything else stays exactly the same. Next, if I have any like terms on the same side, I need to combine them. In this case, I have this 2 and this 9 that are both constants and they're both on the right side. So I want to squish those together and combine my like terms. So again, nothing else changes besides that part. So I get 2x plus 11 here. Now I'm going to start doing my inverse operations. I want to get all of the x's to the same side. If for my purposes, I would bring them to where they're positive, but I'm going to do it where they all go to the left. Well, let's do it both ways. So first, let's do it to where we bring them all together as a positive number. I like that way better. Since I'm bringing the x's over here, I'm going to take away the constant from that same side. I end up here, the x's cancel, and I get negative 16 is less than 8x. To get rid of my coefficient of 8, I divide by 8, and then I end up with negative 2 is less than x. Just for formality's sake, we're going to write it backwards though. So remember, this is the same as x is greater than negative 2, and we're going to write it that way with x on the left side. So on my number line, if negative 2 is here, 0, 2, 4, then I'm going to have an open circle at negative 2, and then an arrow going to the right because x is bigger than that. The other way of solving it, so we did it by bringing all the x's to the same side, but that makes some people uncomfortable because of this last step where we have to write it in the other direction. So instead, let's look at what happens if we take all the x's to the left. So we started with negative 6x minus 5 is less than 2x plus 11. So at this point, we're going to bring all the x's to the left, so minus 2x minus 2x. That means the 5 needs to go away. Bring it over here. And we're left with negative 8x is less than 16. And now we're going to divide by negative 8. And as soon as we say divide by negative, that needs to set off a warning that says look at your inequality and flip it the other way. So anytime you multiply or divide by a negative, we need to flip that inequality, and we get x, the inequality flips, now it's greater. 16 divided by negative 8 is negative 2, and we come up with the exact same answer. So it doesn't really matter which of these methods you pick. They do the exact same thing, and like I've said in other videos, this is like the beauty of algebra. As long as you do valid problem-solving steps, you're going to get the right answer, even if it's a slightly different method than others have taken.